All right, guys, here's part two of our 3.3 lecture on derivative rules or differentiation rules. Last section, I talked about this notation, which you can see here at the top, the d dx idea. And I just wanted to say the notation style, we'll say, of d dx, dy dx, df dx, all of this kind of notation is something that will be used greatly in the future if you continue to take calculus courses and beyond. We'll mostly use kind of the prime notation, the f prime and stuff like that. But this notation is called, the Leibniz notation. And that is just after the famous mathematician, Leibniz, who created it. So nothing too crazy there. So last time we talked about the derivative of constant. Now we're going to talk about the most powerful derivative rule that we get. And it is so useful with polynomials and with so many functions, because so many of the functions that we see occur in the real world are either polynomial type functions or exponential type functions. And so a good chunk of them are polynomials. So it's nice to know how to take their derivative. And this is what's known as the power rule. Big, boom, massive, important guy. Like this one is like, pay attention to this. Okay. So we start out by saying let n be a positive integer. So that just means it is a positive whole number, right? 1, 2, 3, 4, and so forth, right? Not zero, not negative, not fractions, positive integer. If f of x equals x to the n, then f prime of x equals n times x to the n minus 1. Okay. Alternatively, and this is using that Leibniz notation that we talked about. Alternatively, we can say that d dx of x to the n is equal to n times x to the n minus 1. The real difference here, the reason why we say alternatively we even give this in the first place, is not everything is given a function name. Not everything is we're working with is like, hey, here's this formal function with this function name, and we're going through all this stuff. Sometimes it's just very simply, here's an expression, we've got this thing, we need to take the derivative of it, so we use this Leibniz notation for that. So we could do some quick kind of proofs of it and do some kind of generic things, but no one wants to do that because that's just a big mess. But what we can do is we can kind of learn from the problems that we've done, right? We did before, right? In part one, we found that if f of x equals x squared minus 3x plus 6, then f prime of x is 2x minus 3. And we have some other things and stuff like that. And this is kind of using that, but it's also using another rule that's really important. And we talked about this with limits. This was a limit rule that we had, but we want to talk about this with derivatives because it's very important with derivatives as well. So we have the sum difference and constant multiple. Multiple rule. Big thing. It's just really kind of three rules, three separate rules. We're throwing them together because they're really kind of similar. They're really just kind of basic and really, really helpful and useful. Um, and so what we say is for all of these, we're just going to define, we're going to say let f of x and g of x be differentiable functions. So keep in mind what that means is that we're able to take the derivative of these. So wherever it takes the derivative, they're differentiable everywhere. It's not like an absolute value function which isn't differentiable at that turn. And so we have these two functions which are differentiable, so their derivatives exist. That's what that tells us. And instead of a period. And k be a constant. So we have f and x are differentiable functions and k is some constant. It doesn't mean it's an integer, it doesn't mean it's positive, it doesn't mean negative, that doesn't matter. It's just a constant value. So then with these in place, all of the following hold true. So say the sum rule. Okay, come on, wake up. There we go. So kind of verbally, we can say that the derivative of the sum of two functions is the sum of the derivative of the two functions. And what you'll see here when I write this down in just a sec is very simply that means that derivatives are essentially distributable across addition. So if we have dx of f of x plus g of x, that's equal to ddx of f of x plus ddx, get rid of that triangle, ddx of g of x. So we could also kind of, another way to kind of state this, if j of x equals f of x plus g of x, then j prime of x equals f prime of x plus g prime of x. Okay. We're going to do some examples with this. This is what really helps us with the derivative of polynomials, but all three of these are going to combine to give us derivatives of polynomials being snap easy questions that are just like trivial almost once we get comfortable with these rules. The difference rule is very similar, right? So instead of saying the derivative of the sum of two functions, it's simply the derivative of the difference of two functions. So derivative of the difference of two functions is the difference of the derivative of the two functions. So again, ddx of f of x minus g of x is equal to dx of f of x minus dx of g of x, right? Or we could say if j of x equals f of x minus g of x, then j prime of x equals f prime of x minus g prime of x. Okay. So far what we basically get is that if I take the derivative of a difference, let me throw some parentheses and I'll do that. Yeah, I did that up there. If we are taking the derivative of the difference of two differentiable functions, we can simply take the derivative of each piece on its own and subtract those derivatives. Pretty straightforward and simple. And last piece is the constant multiple rule. Or constant multiplier rule, whatever you want. And that just simply states that the derivative of a constant times a function is the constant times the derivative of the function. So we say that dx of k times f of x, remember k being a constant we defined earlier, and f is still our same differentiable function, is just k times ddx of f of x. Or if j of x equals k times f of x, then j prime of x equals k times f prime of x. So I'm not going to go into the proof of any of these. If you would like to look through your book more, you can definitely see that and kind of how that comes about. But what these really say is that if I take the derivative of this big, especially polynomial expression is where this really comes in handy. Combining these rules with the power rule, it makes it so easy. So let's look at the two examples we did before. So we have f of x equals x squared minus 3x plus 6, right? And we found using the limit as h approaches 0 definition of derivative that f prime of x is 2x minus 3, right? We found that using that limit form. But now applying these rules, okay, so I want to find ddx of f of x. Well, that's equal to ddx of x squared minus 3x plus 6. Now, just like any other rules in math that we've covered, things like sum and difference rules and stuff like that can actually be expanded, right? They're defined with two things, right? If I say I'm taking this thing plus this thing, then I can do that. But if I have multiple things, we can just say, okay, well then, so in this example here, essentially this is our first piece and this is our second piece. So we can use the difference rule to say that this is the derivative of x squared minus the derivative of 3x plus 6, kind of that sort of idea. But we can just kind of use that to say, okay, so we can just distribute this all the way through. So then I get, using the sum rule and difference rule, we get dx of x squared minus dx of 3x plus dx of 6. Now I want to use one more rule here before we start evaluating any of these limits, and that's the constant multiplier rule. So that means the ddx of x squared stays the same, but now instead here of having 3x, I get minus 3 times dx of x, plus dx of 6. Now we just use the power rule on this first piece and second piece. And so the derivative of x to the n, right, if we remember, ddx of x to the n is n times x to the n minus 1. So here our n is 2, so this becomes 2 times x to the 2 minus 1 minus 3 times. Now remember, if there is no derivative, we have a derivative of 1. And so we get the 1 pulled out front, and then we get x raised to the 1 minus 1. And I know some of you guys are going like, hey, we don't need, like, this is all, yes, I'm writing over way too much. But that's for a reason. And then for this last piece, we use the constant rule, not the constant multiplier rule, but the constant rule that we talked about in part 1 of this video, which says the derivative of a constant is 0. So we have now taken all the derivatives. Now what we need to do is simplify our expression as much as we can. And so when we look at this first piece here, we have 2 times x to the 2 minus 1. The 2 is just going to stay there, as is the x. And 2 minus 1 is just 1, so we leave the exponent off. On this next piece, I have negative 3 times 1 times x to the 1 minus 1. Well, we know 1 minus 1 equals 0. And x to the 0, or anything to the 0, is 1. So we get negative 3 times 1, which is just negative 3. And then plus 0 does nothing, so we get this. So what we end up with is that f prime x plus 2x minus 3. And so if we look back at the original function, right, remember that f of x was x squared minus 3x plus 6. We just go, cool, we're going to use the power rules here and constant rules in sum addition. We're just going to take each piece, we're going to do the derivative. I just move the exponent down in front and take 1 off of the exponent. So that 2 came down, giving me a 2x, and then I take 1 off, so take 1 off of 2, you get 1. The next one I have negative 3x, so take 1 off of, so take 1, put it in front, does nothing because they were multiplying by 1, doesn't change anything. And then we take the exponent of 1, down 1 to get 0, and that makes it go away. So we get negative 3, and 6, derivative of 6 is nothing. And so I want to make sure I get this right. I'm going to scroll back up in my notes to where we were last. Up here, sorry. So 3x cubed, 4x squared, minus 8x plus 15. I've already forgotten it. So we'll get close. So g of x equals 3x cubed minus 4x squared plus 8x minus 13 plus 13. I'm not sure. I don't remember which one, but it doesn't matter for the derivative. So from this, using these rules, g prime of x is really easy, right? In our heads, this is something that I expect when I ask you this question on your next test, you will give me absolutely 0 work. And I'm perfectly happy with that. This is a problem that should become a mental math problem for you. Looking at this, 3 times x cubed minus 4x squared plus 8x minus 13, and taking the derivative of that, we just go, okay, cool. I have 3 times 3 gives me 9. And then I take 1 off the exponent, so it was 3. Now it's 2. I have negative 4x squared, so I have 2 times negative 4 gives me negative 8. Take 1 off the exponent, so it was squared. Now it's 1. We don't need an exponent. 1. Our next term, I have plus 8x. Take 1 off the exponent, or bring the 1 down, right? It doesn't do anything. It just multiplies 8 by 1. Then we have 1 less than that, which is 0. X to the 0 is 1, so we just get plus 8. And then minus 13 is a constant, so it goes away. So there's our derivative, right? So we can just do this using these derivative rules, and it is so easy and so quick. So that is kind of how we're going to be working through this. I don't really want to beat this one over the head. I don't want to do 50 different examples, but it's kind of a nice, simple thing. Now, I want to do an extension on the power rule. So call this the extended power rule. Now, if you remember, for the power rule, we said that let n be a positive integer. That meant it had to be a positive number, right? So like x cubed, x squared, x to the 16th, anything like that. Now, what if n is negative? What happens then? How do we deal with that? Well, the same way. So we let n be a negative integer. Okay. So if n is a negative integer, then d dx of x to the n is equal to n times x to the n minus 1. It's that easy, right? So it's the same thing. But we have to kind of be careful with this, and we have to be kind of aware of some of the exponent rules, right? We have to recall, if you will, that if I have x to the negative n, I don't like the size of that, x to the negative n, that is just 1 over x to the positive n. Now remember, this is an equal sign. Equal signs mean we can go both ways. I didn't like the way that looked because I'm being picky right now myself. So that means if, let's say, g of x equals, we'll be nice to ourselves, go over something, 1 over x squared. Let's find g prime of x. So we need to find the derivative of this. Well, the problem is 1 over x squared is not in the form for a power rule. Our power rules both were in the form of x to the n. This is not x to the n. And so I need to rewrite this so that it is. So to find g prime of x, I need to consider that g of x, which is 1 over x squared, is actually x to the negative 2. Hopefully this is like, yeah, obviously we got this. This is super easy, and that's what I'm hoping. But if it's not, right, these exponent rules are definitely crucial in this. So then we have this in the right form. So from here, then g prime of x is going to be negative 2 times x to the negative 2 minus 1, which is negative 2 times x to the negative 3, which then if we want to write this, and this is something that you will probably want to do for especially homeworks, rewrite this with a positive exponent. So we get negative 2 over x cubed. And so that's our extended rule, okay? Now, just because I'm sure somebody's probably thinking it, right? Because we've said, well, if n's positive, if n's negative, what happens if n equals 0? Then we get x to the n is equal to x to the 0, which is equal to 1, which is a constant, thus its derivative is 0. So we can't like just continually apply this rule. So with like higher order derivatives, it's really nice. We can kind of apply that to a point until we get down to where the highest power of n, highest n is 1, and then it goes to a constant, and then from there on, our derivative would be 0 after that. And so then it's just the constant function 0. You're taking the derivative of another constant, and it doesn't do anything. So that is our lovely power rule, our extended power rule, and then the sum difference and constant multiple rule. That is going to be really useful in finding derivatives of polynomials. And we'll also use these, we'll see these come up with some other functions that we're going to deal with in part 3 of this lecture video. I know you're like, why do we have so many parts? Mainly because I didn't want to give you guys a 50-minute lecture video. That seems daunting to watch. So the next part, we are going to cover the product rule and then the quotient rule. So that is it for this bit. See you next time.